Good evening, class. We are looking at college algebra practice test number 3, module 3, covering chapters 5 and 6. And here's the second part of chapter 5, polynomial and rational functions. Let f of x be x over x minus 2. Sketch a graph of f using technology to determine whether f is a 1-to-1 function. I'm assuming everybody by now knows how to graph it. It's very easy. You can come up with the vertical asymptote, horizontal asymptote, and so on. So we graph it, and yes, it's a 1-to-1 function because it passes HLT, horizontal line test. Horizontal line test. It's important to understand that, okay? And of course, I hope you see that the degree of the numerator is 1, the degree of the denominator is 1, so the coefficient is 1 here and 1 here. So y equals 1 over 1, or y equals 1 is a horizontal asymptote, x minus 2 equal to 0, x equals 2. Those are the asymptotes. So vertical asymptote, horizontal asymptote, and it's a 1-to-1 function. If it's a 1-to-1 function, find its inverse. So how do we find the inverse? Remember, f of x is the same as y. We call it y because it makes it easier to deal with. Then we interchange x and y. So this becomes x, this becomes y, this becomes y. Cross product. So this times this times this. So x times y, xy, x minus 2 is minus 2x, their product, and this is y times 1, y. Because we are solving for y, we are going to move this y here, negative 2x there. So as you move, I say move things around, that means, just add or subtract. That's the other one. So you move this, becomes positive, move this, becomes negative. So xy minus y, and you factor the y out, and you divide by x minus 1, and you call it f inverse. So it's very straightforward, okay? Y equals f inverse of x is 2x over x minus. And I hope you see you can just graph it. The vertical asymptote and horizontal asymptote, they interchange because now the vertical asymptote x equals 1. The horizontal asymptote, remember, this has degree, this has a coefficient 2, this has coefficient 1. 2 over 1 is 2. And so you have the graph here. Here's the vertical asymptote, here's the horizontal asymptote. And as I mentioned, let me erase my work because I need this space. Notice VAs and HAs, vertical asymptotes and horizontal asymptotes, everybody. So what do we notice here? X equals 2 is the vertical asymptote, which corresponds to y equals to the horizontal asymptote here. Horizontal asymptote here is y equals 1, corresponds to the vertical asymptote for its inverse. And that's the idea that we want to recognize. And now, as far as the domain of f, when we go back to this one, all real numbers except 2, because x minus 2 equals to 0, x equals 2. So the domain is minus infinity to 2, union 2 to infinity. What about the rest of them? I hope you recognize, because the two functions are inverse of each other. Domain of f is the range of f inverse. So we write the range of f inverse is minus infinity to 2, union to 2 infinity. What about domain of f inverse? Here's the f inverse. All real numbers except x can't be 1. X minus 1 equal to 0. X becomes 1, and that must be excluded. So from negative infinity to 1, union to 1 into infinity is the domain of the inverse function, which is the range of f minus infinity to 1, union 1 to infinity. Solve the following inequality, graph the solution set, and write it in interval format. So to do so, we are going to factor the top and the bottom. So the top, you want two numbers. The product is negative 18. The sum is negative 3. So you get positive 3 and negative 6. That's the first thing. And of course, if you can simplify, you must. We can't. So basically, we draw a number line from negative to positive infinity, and we put everything that makes the top 0, everything that makes the bottom 0. So you have a number line, okay? minus 3 makes, and let's call this f of x. This is now, for short, we call it f of x. So the function, this rational function, is 0 when x is minus 3. It's 0 when x is 6. And at x equals minus 2 is ud, undefined. Let me just write it out. And by the way, uh, you need to use TPs, short for test points, to see what happens in between. So, for example, here we could choose maybe minus 4. Between this one, maybe minus 2.5. And between these two is the easier, the easiest number would be 0. And beyond 6, any number. For example, 7, 10, 20,000, who cares? Somewhere there. Now, what matters is that, because if you look at this one, the degree is 1, the degree is 1, the degree is 1. In other words, it's odd. If you find one of those regions, the rest of them will alternate. If any of them has degree 2, then both sides would be the same. So let's go with the 0. If I plug in 0 here, and by the way, it might be easier to put it here. If I put 0 here, this goes to 0, 0, 0. You get minus 18 over 2. So if I put 0 in here, I get negative 9. I don't care for the number. I just want the sign. If I get negative here, then they alternate, positive, positive, negative, or try those test points into this format or in this two, in this format, however the format that you want to try. Now we go back to answer the question. We want this to be larger than or equal to 0. That means look for positive. So here it's positive, and here is positive. So from -3 to -2, union 6 to infinity. Now, because we have the equality, now, and -3 makes it 0 is okay, but -2 belongs to the denominator, is always undefined. So that's not okay. That's a parenthesis. 6 makes it 0. That's okay. So we write it in the following fashion. From -3 to -2, union 6 to infinity. And so we locate -3 and -2 anywhere in between, and then we locate number 6 and anything to the right. And the endpoint is included. Number 6 is included. Okay. Number -3 is included. -2 takes a whole or parentheses. You can go either or. Okay. So that's very straightforward, everybody. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x is a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way a sub 0. Eventually, it will look like y equals a sub n x to the power of n. That's what is going on, and that's important. So the end behavior means ultimately this leading term will take over. So here's what happens. If the degree is even and the leading coefficient, this is positive, ultimately looks like y equals x squared. It opens up. That means f of x goes to infinity, x goes to negative infinity, and f of x goes to positive infinity, x goes to positive infinity. If you're dealing with the even, but it's negative, this number is negative, just think of minus x squared. It opens down, which means f of x goes to negative infinity in both cases, whether x goes to negative or positive infinity. However, what happens if the degree instead of even is odd? Okay, so think about this. Either will look like y equals x cubed or y equals minus x cubed. Those are some of these essential functions. We know how the graph looks like, or at least we are supposed to. Therefore, in this case, x goes to infinity, so does y. In this case, x goes to negative infinity, so does y. But y equals minus x cubed. If this is negative, notice minus x cubed. As x goes to infinity, y goes to negative infinity. As x goes to negative infinity, y goes to positive infinity. And that's the idea. This is known as the end behavior. We also have a theorem regarding multiplicity. Behavior near a zero. Multiplicity of zero. When we have x minus c to the power of m, m is considered the multiplicity, how many times it repeats. If m is odd, this exponent is odd, f crosses the x-axis at c0. If it's even, it doesn't cross, it bounces back. For example, here it crosses over the multiplicity 2. In this case, multiplicity is 3. So the higher the multiplicity, the flatter the curve is at 0. But it crosses. The sum of the multiplicities, and that's important, is the degree of the polynomial function. Number of zeros theorem, a function defined by a polynomial of degree n has at most n distinct unique complex zeros. So there's a lot of information here. Now, I'm going to use that to graph a function. For example, I'm going to graph the following. And we're going to use the end behavior and behavior near an x-intercept. Ultimately, you need the x and y-intercept if need be. Okay. So the very first thing we try to do, let's put it in factored form if possible. And if we put these two together, we can say x squared times x minus 5. And this one, just take the negative one out. The reason we do that, we are looking for this common factor. So it's x minus 5 times whatever is left, which is x squared minus 1. And as you know, x squared minus 1 is x plus 1, x minus 1. So we already have all the x-intercepts. See, the exponent is 1, the exponent is 1, the exponent is 1. When there's no exponent, that means the exponent is 1. All of them have multiplicity 1. This is at 5, 0. This is negative 1, 0. This is positive 1, 0. So those are the 3 points. Now, what about the y-intercept? It's easier to go to this one. Y-intercept, that means x is 0. Everything is 0 except this one. So 0, 5. Okay, so we have all the intercepts. Now, the end behavior, I hope you see that the leading term is x cubed. So the end behavior depends on this exponent n equals 3, which makes it odd. And a sub n equals 1. See, the coefficient is 1, which makes it positive. And in short, it means it looks like the end behavior looks like y equals x cubed. So this, the first and the third quadrant. In other words, as x goes to negative infinity, so does y or f of x. As x goes to positive infinity, so does x or y. Both of them go to infinity at the same time or negative infinity. So that means really this is, sometimes we use, we say this one and this one. These two arrows mean the end behavior looking like that. And that is, of course, a better graph with a little bit more details, everybody. Now, a quick recap for this. You factor it and you find 3 x-intercepts. You have 1 y-intercept and you have the end behavior. Clearly, it gives you the graph. If we look at this one, g of x is x minus 2 quantity squared times 2x plus 3, and we want to graph it in the same fashion, we can go with the intercepts, and I hope you see that this is 2, 0, and this is negative 3 half 0. This one has multiplicity 1, this has multiplicity 2. So x-intercepts. We have 2, 0. Multiplicity is 2. That means it refers to this exponent, everybody. Okay. This one, set it equal to 0, x equals negative 3 halves, but multiplicity is 1, the exponent is 1. So you have those two pairs. And normally, when the multiplicity is even, we draw a double arrow, meaning when you draw that, that means when you hit this point, you can't cross. In other words, if you come on down here, you can't cross, go back. If you come on from down here, you have to bounce back. And that's the idea behind that. Now, Let's go with the y-intercept, and to find the y-intercept, you put 0 here. Let's just quickly see what we get. So if I put 0 here, I'll get minus 2 squared times 3, which is minus plus 4, right? Minus 2 squared times 3, which gives you positive 12. So 0, 12. So we locate 0, 12. And what I want you to notice is we are looking for the leading term. I hope you see that this becomes x squared, and it doesn't matter what. Let me just erase my work so I can show you what I'm talking about. So this becomes x squared. The rest is not important. When you multiply these two, you get 2x cubed. So we are interested in 2x cubed as a leading term. You can write the rest of it. It's really not that big of a deal. But when you write the leading term, it gives you, again, a lot of information. Everybody, n is 3, which makes it odd. A sub n is 2, which makes it positive. And so in essence, we are talking about this n behavior. That's the concept that I want everybody to understand. So having said that, again, let me erase my work. So x goes to negative infinity, so does f of x, and x goes to positive infinity, so does f of x. So we come on down here, we hit this one, but we can't cross, we have to bounce back, and then like so. Now, one thing I want to tell you, where do we end up? When we go back, do we go like this? Do we go like this? Or do we go just like that? In other words, there are 3 possibilities for the maximum, and then we may go like that, or let me erase that. We may go like this, but we don't know that really without calculus. That's what happens with the calculus. We have a, better result accordingly. So that's what we learn in calculus. We're going to discuss that when we come across it. So having said that, now we want to look at this one, and what is the least possible degree of a polynomial? Write an equation for the polynomial graph. Okay, first and foremost, let's discuss a couple of things. Turning points, where the graph of a function changes from increasing to decreasing. For example, this is decreasing and it's increasing. This is one turning point. Then increasing, decreasing, this is the second one. Decreasing, increasing is the third one. So that's the idea. So turning points, where the graph of function changes from increasing to decreasing or vice versa. The number of turning points of the graph of a polynomial function of degree n is larger than or equal to 1 is at most n minus 1. Local maximum point, highest point or peak in an interval function value at the points are called local maximum. So this is a local mean, local max, local mean. That's what we are saying. Okay. And this happened to be an absolute minimum because no point has a smaller y coordinate. A local maximum point, lowest point or value in an interval. Function values at these points are called local minimum. Plural of extremum, including all local maxima and local minima. So, okay. Now, how many do we have here? 1, 2, 3. Then we must have 4. Why is that? Because if it's n minus 1, okay, n minus 1, 1, 2, 3 equals 3. So n must be 4. Okay. We have 3 terms. Again, let me erase my work, everybody. All right, we'll write an equation. So we have 1, 2, 3. X-intercepts. Okay. So this is number -3. Let me write that. This is -3. This is +1. And the multiple, maybe I put it, okay, let me just erase my work again. Use a different color. So this is number -3. This is number 1. And the multiplicity. This crosses. the x-axis. This one crosses the x-axis, multiplicity 1. This one doesn't cross. As it hits, it has to bounce back. So the multiplicity is even. So these are multiplicity 1. This multiplicity even. 2, and so on. And it happened to be that 2 is enough because, so this one gives us x plus 3. This gives us x plus 2. This one gives us x minus 1 squared. Everybody, squared. So we put some number in between like a. So that's why I put the double arrow here. So f of x, the function is a, something we don't know, times x plus 3, this one, x plus 2, this one, and then x minus 1, this one. Why is it squared? Because it bounces back. The multiplicity is 2. So all you have to do, pick an easy point. You can pinpoint an easy point. Obviously, this is 0, 3. Plug in and find the a. So let's replace the x with 0. So we get 3 here. We get 2 here. Minus 1 squared times a. And this is 1. So we have 6a. So a must be 3 over 6. Or 1/2. And therefore, the final answer, f of x is 1/2, parentheses x plus 3, parentheses x plus 2, parentheses x minus 1 quantity is good. Of course, you can multiply them out if they ask you to do so. Find the degree leading coefficient and maximum number of real zeros of the polynomial f of x equals 2 plus 3x to the power of 6 plus 4x to the power of 7 minus 6x. Also describe the end behavior or long run behavior. Again, reminding you of a polynomial. We've already discussed that. Polynomial is in this format. P of x is a sub n x to the power of n all the way to a sub 0, where a sub I is a real number and the exponent is a whole number 0, 1, 2, 3. A sub n is called the leading coefficient. A sub n x to the power of n is the leading or dominant term. A sub 0 is the constant. Of course, there is not much brand new here. So the very first thing is to put this in descending order. To put this in descending order, this comes first, this one second, third, and the last. Okay. So in other words, 4x to the power of 7 plus 3x to the power of 6 minus 6x plus 2, which makes 4x to the power of 7 a leading term. Leading coefficient is 4, and the degree is 7, everybody. Degree is 7. Leading coefficient is 4. Maximum number of real zeros, 7, because the degree is 7. And notice this is odd and this is positive, so the behavior is ultimately like x cubed. Leading term is 4x to the power of 7. N is 7. What matters is that it's odd. A sub n is 4. That means what matters is positive. So this is positive, this is odd, ultimately looks like x cubed, which means as x goes to negative infinity, so does y or f of x. As x goes to positive infinity, so does y or f of x. That's the meaning of it, everybody. Use number of zeros theorem and Descartes' rule of signs to discuss real zeros of f of x. Fill up the table. F of x is given as 3x to the power of 7 minus 4x to the power of 4 plus 3x cubed plus 2x squared minus x minus 3. So a couple of things that are obvious. Obviously, this is in descending order, and that's good. We want it. So secondly, this is the leading term, 3x to the power of 7. And therefore, because the exponent is 7, the maximum number of zeros must be 7. And so we have positive real zeros, negative real zeros, imaginary zeros, and the total. Well, the total is 7. So what else? Well, let's look at a theorem. Descartes' rule of signs determine the number of positive and negative zeros. Let f of x be the polynomial function f of x equals a sub n x to the power of n all the way to a sub 0, with terms in descending powers of x. A, the number of positive real zeros either equals the number of variation in sign occurring in the coefficient of p of x, or is less than the number of variation by a positive even integers. We're going to stop here. I'm going to continue with part B in a moment. So part A says, basically, look at part A says, look at the sign change. Notice this is positive, negative, and so forth. Let's do that. So we are looking at this part. Just part A, never mind the list. So I'm going to read it one more time. The number of positive real zeros either equals the number of variations in sign occurring in the coefficient of p of x, or is less than the number of variation by a positive even integer. So again, positive 3, negative 4, positive 3, positive 2, negative 1, when we don't have a coefficient of negative 1, negative 3. So we just are interested in sign. So the number of positive real zeros either equals the number of variations. So how do we vary? From here to here, there's a variation because positive becomes negative, negative becomes positive. But there is no variation here. But there's a variation here, and there's no variation here. So we have number 1, number 2, number 3. There are 3 variations, everybody. So there goes number 3 here. Positive real zeros. What about negative ones? Let's read on. The number of negative real zeros either equals the number of variation in sign occurring in the coefficient of p minus x, or is less than the number of variation by a positive even integer. What does it mean? That means now go back to the function and evaluate f of minus x. So if I put minus x, because this has exponent 7 becomes negative, so minus 3x to the power of 7. This one doesn't change. Become minus x to the power of 4 or x to the power of 4. So minus 4x to the power of 4. This changes to negative 3x cubed. This is plus 2x squared. This negative becomes positive. This negative 3 doesn't change. There you have it. Now, clearly negative, 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 positive, positive, negative. So let's just look at the signs and the signs only. Now, this one says look at the change in the number of variations. From negative to negative, no change. Negative to negative, no change. Negative to positive, we have 1 change here. Positive to positive, no change. Positive to negative, 1 more change. So we have 1 and 2. 1 and 2. There are 2 changes here. Therefore, this answer is true. Now, we have 3 positive zeros, 2 negative zeros, but the total is 7. So the rest must be imaginary. A plus minus B I. That's what we mean. So 3 and 2 is 5. Subtract it from 7, you get 2. So that's what happens. Now, the next thing that we want to pay attention to, it says, or is less than the number of variation by a positive even number. The same thing here. So 3 can go down by 2 becomes 1. 2 can go down by 2 becomes 0. So if this becomes 1, this becomes 0, this must be 6. Or we keep the 3, and this just goes down to 0, in which case, if this is 3, this is 0, this must be 4. Remember, the total 7 it remains unchanged. Okay. Or maybe we keep the 2, we don't change that, but this one is 1. So 1, 2, then this is also 4. And those are all the variations. All right. What is the least possible degree for this polynomial? Okay, 1. Peaks and valleys. 1, 2, 3, 4. 1, 2, 3, 4. So at least 5. because there are 4 terms. Write an equation. Well, I'm going to write the intercepts here, 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 and here. Now, over here, -4, we get x plus 4. Over here is -1, we get x plus 1. Over here is +2, we get x minus 2. Over here is 4, we get x minus 4. Multiplicity is 2. Let's just look at it one more time. Crosses, 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 can't cross here. This one has multiplicity 2. So we write f of x equals a something times x plus 4 times x plus 1 times x minus 2, and this one is x minus 4, quantity squared. And I hope you recognize that the degree is 1 here, 1 here, 1 here, 1 plus 1 plus 1 is 3, and 2 is 5. The degree is 5. Now, pick up an easy point. Of course, you can see the y-intercept that is at 0, 2. So replace the x with 0, f of x or y with 2. So 4 times 1, 4 times -2, -8 times 16. -128 divide by 2. 2 divided by -128. A is a 2 divided by -128 for -1/64. Therefore, f of x is -1/64 times x plus 4 times x plus 1 times x minus 2 times x minus 4 squared. That's the final answer.